Hi class, we are now on chapter 20.4. We're going to look at standard electrode potentials. So in this chapter, we're going to be looking at the cell potential. So we're going to start doing some calculations here to understand exactly what we're looking at. So remember, a cell potential is a measure of the driving force of that reaction. And the cell potential depends on the concentration of substances and temperature of that cell. So we're going to be looking at different reactions that happen and the values that they give. Now remember, voltaic cells, they produce a flow of electrons. Remember, there's a light bulb on top. That's the external wire that's connected by a wire that, I think I said wire twice, where the electrons flow. And we have a salt bridge that allows the flow of ions, so there's no charge buildup, and allows this to keep happening. The electromotive force associated with the flow of electrons is measured as the cell potential or voltage. This is, remember, the cell potential is a measure of the driving force of the cell reaction, or the potential difference in the difference between 2 points, if that makes it easier, and it's measured in volts. Okay, so chemists choose a specific cell. So we cannot measure, it's not possible to measure the potential of a single electrode. So only the cell potentials can be, the whole thing can be measured. But what if we can fine tune, in a sense, one of them and make it arbitrarily equal to 0, then the other cell, or the other cells, because you can actually do more than 2 cells, even though that's what we've been talking about, then you can figure out the values for the other one. So if you have 2, you make one 0, then the value that's produced must be from the other one. And that's what we're talking about, so you can measure it. And this is where the standard hydrogen electrode come from. I don't know if they say it's she or SHE. I don't know. I'm assuming it's she. But standard hydrogen electrode, I prefer. So what happens with this? So again, if we want to measure the other cells, then what we do is we use like a reference, and we arbitrarily assign this reference electrode potential equal to 0. And that way we can determine what the other potentials are, because this one's equal to 0. So this is the standard hydrogen electrode, and it has a potential of exactly 0.00 volts. And it's under standard state conditions. So this standard hydrogen electrode, it consists of 1 molar of hydrogen chloride with hydrogen gas at 1 atm bubbling through the solution. So that's what you see, there's little bubbles here, excuse me. And it has an inert platinum electrode. So the platinum electrode will help with the electrons, but it's not actively playing a role in the reaction. And then, as you can see here, here's the HCl, here's the hydrogen gas at 1 atm. So standard hydrogen electrode is what we use, and we assign the value of 0 volts to it. So if we look on this next page, so as you can see, there's a reduction of hydrogen gas, hydrogen protons to hydrogen gas under standard conditions. So let's take a look here. You can see there's a salt bridge for the other half cell that would be connected, and then the HCl, which is in ionic form, so it's just the protons. The platinum will help this as an inert electrode, and then we have the hydrogen gas at 1 atm. So cell potential. So when we look at this here, we're looking at 2 different reactions. We have at the anode, we have zinc, and which is oxidized, and we have the cathode, we have the hydrogen that will be reduced. Now, as you can see with this reaction here, it's a negative 0.76 volts, and this one's the 0. If this is a spontaneous reaction, then the value of the overall will actually be positive. So the value, even though this is a negative here, the cell potential of the cell potential of the overall is positive for a spontaneous reaction and negative for a non-spontaneous. So if we look at this here, this is actually for the measured potential, cell potential for this is 0 positive, so a plus sign, plus 0.76 volts. It is positive in the overall. This reaction by itself, the oxidation is negative, which is what we want in the end. We want that to be negative. It's actually a lower number than the 0 number. And that means that it's going to be spontaneous. It's a strong reaction. It's going to allow those electrons to leave that zinc solid, and it's going to transfer to the hydrogen gas. So the potential energy increases as you can see, but the value actually, we want this overall. So I know that sounds kind of weird that this one reaction here is positive, this negative, but the overall reaction has to be positive in order for it to be considered spontaneous. So as it states in your book, with this one, the zinc is the oxidation has a more negative voltage than the cathode. So the electrons are going to spontaneous flow from the anode to the cathode, which is, so we want values that are lower than the 0 in order for them to be spontaneous. So the potential for the zinc ion electrode is negative. The negative potential, I'm reading it straight from your book, indicates that an electron at the zinc or the oxidation electrode has greater potential than it does at the standard hydrogen electrode. So the more negative the electrode potential is, the greater potential energy of that electron on that electrode, because negative charge repels electrons. So the electrons won't go to that electrode because it's going to repel them because there's already electrons there. Okay, so this slide is actually wrong. These values should be switched. If you look on your page 908, this is negative 0.76 and this is positive 0.34, which is what you see here. So this down here doesn't make sense matching this, and that's why this might seem confusing. But if you look in your book, these values are written out correctly with the negative value and the positive value. So in this case, zinc has a stronger tendency to oxidize. Why? Because the value with it is a negative 0.76, which copper is actually a plus 0.34. So if you want to look at these in values, this is actually a higher value than the 0. So it is, and it's an anode. So this is going to be non-spontaneous because this is not going to be oxidized as easily as zinc. So it's not going to give up those electrons as easy as zinc would. It's got a more positive voltage than the cathode. So the electrons, they're not going to spontaneously flow from the anode to the cathode. So again, this part here, I just caught it right as I'm recording it. So this number is this number, and this number is what we showed you on the previous page. It's a negative 0.76. And then here is a list of some of the reactions. These are all done as reductions. So if they're reductions, you can see that these are done as what? Reductions are gaining electrons. So that's how they're all set up in this Treatises. So these are all positive values here. So when you look at some of these, you can see that some of them are negative and some of them are positive. So the more positive value, so if electrode, let me see if I can explain this right. The electrode in any half cell that has a greater tendency to undergo reduction, which is gain electrons, is positively charged relative to the standard hydrogen electrode. So if standard hydrogen electrode is 0 and these are positive, then these have a greater tendency to actually gain electrons and not be oxidized and lose the electrons. And just as we've looked at standard conditions for other things, this is still when you hear the word standard, these are any solids and liquids are pure substances. These are the standard conditions for this to measure biochemical reaction. Let me repeat that. Let me correct that. To have a chemical reaction to determine the measured voltage, we have to have certain standard conditions. So solids and liquids are pure substances. Any solutes have a concentration of 1 molar, and gases are at 1 atm pressure. And through this, then we can then set these standard conditions to determine the values that we need to determine. So here's a perfect example. If we know that we're using a standard hydrogen electrode here, we know that this is 0. So any of the values that are given in the voltmeter are going to be from what's taking place in the other half cell reaction. So that's how we can determine. We can make this one 0, excuse me, then we can determine what the value is for the other half cell. So half cells potentials, again, standard hydrogen electrode reduction potential is defined at exactly 0 volts. We compare that half reaction. So we can compare the reaction, the standard hydrogen electrode, or that reaction that occurs there, which is 0, and what is taking place there is a reduction of a hydrogen ion or proton to hydrogen gas, and this is under standard conditions. So half reactions that have a stronger tendency to be reduced, which means gain electrons, have a higher positive value than the standard hydrogen electrode, which is 0. So it has to be anything above 0, it's a positive value. Anything that is stronger towards oxidation has a negative value compared to the standard hydrogen electrode. And how do we determine this? Well, we have for an oxidation half reaction, we have an oxidation here. We can plug in the value and we can see what the reduction, the value is for the reduction and the oxidation. So here's the thing, you're just switching the signs. It's not really complicated with that. And then we have an overall. So this should be cell, not call. It's funny how I notice this stuff only after I start recording. Okay, so we take the value for the oxidation and reduction, and this is where we get the overall, the cell potential, and it equals the difference between the two electrode potentials from the oxidation and the reduction. So we can plug this in and we can determine, and this is called the standard cell potential, and this should say cell, standard cell potential. It is the EMF of the voltaic cell operating under the standard state conditions, which are 1 molar concentration, gas pressures at 1 atm, and the temperature has a specified value, and it's usually 25 degrees Celsius. Here is a list, and you can see anything that is positive. So these have a high tendency to be reduced, and that means gain electrons. If we go to the next one, here's the standard hydrogen electrode, which is 0. And anything below this has a tendency to be oxidized. So if you go on this side, you can see that these tend to be oxidized. They're not going to tend to necessarily gain electrons. They want to lose the electrons, where anything on this one wants to gain it. Now this is interesting. So here is the breaking point. So anything below this will lose electrons, and anything above it will gain electrons. However, we have this little fine line here of nitric acid, which I know it doesn't look like nitric acid, but that's exactly what this is here. And there are certain things that can be reduced, excuse me, it's going to be covered on the last slide, but there are certain things that can be oxidized by the nitric acid, but not by the water. So anything that's below this, but above the standard hydrogen electrode, can actually be reduced by the nitric acid, but will not be, oxidized by the water, because anything above it isn't this is not as strong as that. It's going to be, let's think of it, it's going to gain electrons. It's not going to reduce, oxidize them. But anything below this, nitric acid can interact with and cause them to lose their electrons and be oxidized. So it's kind of a hierarchy kind of thing, which I'll cover on the last slide. Okay, so here we have we're looking at calculating cell potentials under standard conditions. So when we're gonna take our values, we're gonna look at the half cells, and then we're gonna be able to see what we can do through the difference of the cathode and the anode. Now these values are intensive, and what intensive means, it doesn't matter the amount, it matters on what it is. So think of density. No matter what, density doesn't change. No matter how much you have of something, we can still determine what the density is. Okay, higher on the table of standard reduction potentials, the stronger tendency for the reactant to be reduced, which is gain electrons. Lower on the table tends to be oxidized, which is lose electrons. All right, so the standard potential reduction potential is this. Here we go, there's cell. So we take the difference between these. Any reactant or set of reactants in table 21, I did make sure this is correct, will react spontaneously with any product with a lower potential. So this is all hierarchy pretty much. Now if we look here, we have iron, and this goes from iron 3 to iron 2. So this is reduced down. And then we have nickel, that goes from 2+ with the 2 electrons, and it goes to a solid nickel. Now, what does this mean? Okay, so what is this? I should have finished this problem out, and I didn't. But what this means is that anything, any reactant in table 20 will react spontaneously with anything below it with a lower potential. So what does that mean? Let's look at what we have here. We have a negative value and we have a positive value. So this will be reduced down. It has a higher potential to be reduced. This has a higher potential to be oxidized. And let's find them on the list. And this is interesting because some values are slightly different than others. So here we have the iron that we're looking at. We have it here. And it's above the standard hydrogen potential. And the nickel is below the standard hydrogen potential. So because this is below, this tends to be oxidized, where this one tends to be, where is it at? Reduced. So this is a reaction that will actually occur spontaneously, because if we set this up, and that's what I regret I didn't do here. So what we do is we set these values up. Now remember, if we have an overall positive value, this is a spontaneous reaction. So if I set this up, what we do is we take the cathode, which is here, which is 0.77 minus the anode, which is negative. There's a subtraction sign, but so we put parentheses and we went negative 0.227, which makes it a plus sign. So the overall of this is plus 1.03 volts. So this is a spontaneous reaction. So that means that the iron 3 will react with the nickel to produce iron 2 and nickel 2. So remember, this is showing it as a reduction, and we want it as an oxidation. So we can flip this. I have examples. I'll show you on the next slide. Hopefully they set them up right. But this is a reaction. I should have finished with it. But the total of this, when we plug everything in, is a positive 1.03 volts, a spontaneous reaction. Okay, so here is calculate the cell potential of the Daniell cells. So remember, I take these from other slides, and for some reason they're called voltaic cells, Daniell cells. I didn't catch that. I would have deleted it. So if you see Daniell cell, it's voltaic cell, and it's from another book, which consists of zinc half cell and copper half cell. Find the standard reduction potentials and apply this. Okay, so we have a negative 0.76 volts, and this is an oxidation, and here is a reduction. So we have a cathode minus the anode. So we need to know that, remember, when they show these tables, they are shown as a reduction, and we want this as an oxidation. It is as an oxidation, and it will be the anode for this value. So here we plug in the cathode, so we have that value here, minus, and this is what I was trying to say with the negative sign, 0.76, and it produces a positive 1.10 volts. This is a spontaneous reaction. Now, if you look here, it's flipped, and that's what I'm trying to say, is that this is shown as a reduction. We want it as an oxidation, and you see it here as an oxidation. You're just not seeing the electrons that we normally have here in this half reaction, because at the final, we don't include the electrons. But this is exactly how you would solve for that. It's not too hard as long as you remember certain little key things. Okay, so predicting the spontaneity of a redox. Sorry, my phone keeps going off because I have a decoration like right in front of my doorway, and it's windy. Substances listed tend to undergo reduction that are at the top. They're good oxidizing agents. Remember these terms. These are what drives students crazy. Substance listed at the bottom tend to undergo oxidation, and they are good reducing agents. Any reduction reaction is spontaneous when paired with the reverse of any of the reactions listed below it on the table. So anything that's listed above, you need to see where it's listed on below, and if it ends up with a positive value overall, it's a spontaneous. If it does not, it's not spontaneous. So for instance, if we were to flip these and make the copper the anode and the zinc the cathode, and you plug in those same values, you would see that this would overall be a negative value in this calculation, and that means it's non-spontaneous. So it only works one way and is set up a certain way. Okay, so the solution contains both sodium iodide and sodium bromide. Which oxidizing agent could you add to the solution to selectively oxidize iodine but not bromine? This is one that I probably, I think it's in the next thing, and I didn't exactly cover it yet. So I may have actually moved this slide up before the slides. So let me jump to the slide, and then I can tell you. Then we'll go back to that one. So I briefly discussed nitric acid. Nitric acid, almost all metals will dissolve in nitric acid, and it's above the standard hydrogen electrode. So if it's higher in the list of the table, and anything below it, it can dissolve. But with the standard hydrogen electrode, anything above that 0 value, it will not reduce down. It will not oxidize down. So this is where nitric acid comes in, and nitric acid will dissolve metals if it's in its presence. So so what this slide is clearly saying, that metals that are below the standard hydrogen electrode will dissolve in metals, but metals that are above the standard hydrogen electrode will not, except for, now comes in nitric acid. Anything below it, and this is pretty high on the table, can reduce metals out. So that's what we're looking at. So here, I'll do this one, and then we'll jump back to the other problem. Which metal dissolves in nitric acid but not HCl? So remember, this is HCl. Even though it's listed as hydrogen gas, it's still that one. So anything above it, it's not going to be able to interact with. But here, The 0.96 is the nitric acid. Anything below it, it can't. So let's see if we can find these on here. So do we have iron? We have iron, but it's already in ionic state. So this is not the correct one. This is not going to apply. We have gold. Do we have gold anywhere here? We do not have gold, but we do have silver. So silver is the one that's going to react with nitric acid, but it's not going to be oxidized with the standard hydrogen potential. And that's what you see here. So if we go back now, hopefully you saw the answer, but this makes sense. A solution contains both sodium iodide and sodium bromide. Which oxidizing agent could you add to the solution to selectively oxidize, but not iodide, but not bromine? That's got to be nitric acid, because none of these are going to have the same effect. So let's find nitric acid here, and let's see where the iodide and the bromine are. So if we look here, we have bromine right above it. So nitric acid is not going to be able to oxidize bromine. However, if you look here, we have iodide, and it will oxidize iodide. So nitric acid would be the perfect to use there in this.